Hello students, and welcome to this video about test number 2. So for question 1, you will work to generate a plot of the probability function of a binomial random variable with parameters p 0.5 and n equals 30. So your first step is to assign the distribution parameters. N is assigned the value 30, p is assigned the value 0.5. Remember that alternate minus is a keyboard shortcut to insert the assignment operator together with the space on the left and the right. Then you can define the probability function with these parameters set. So f is assigned to be a function of the variable x, and it's d binom of x where the size is n and the probability is p. So note that d binom is the probability function for binomial random variables. Then, one strategy for creating a plot is to build up the data that will be shown in the plot. So M is assigned to be a tibble with two columns, X and Y. X is a sequence from 0 to N by steps of 1. So X here are the possible values of the binomial random variable. And then Y will be f of x. So d binom is a vectorized function. That means you can apply it to a vector and it will apply itself to every element of the vector and return a vector. Now we can create the plot. So G is assigned to be a ggplot connected to the data frame M. And then we can add geom column, and we have a mapping equals AES. So the X aesthetic will be the X column, the Y aesthetic will be the Y column, and the alpha aesthetic will also be the Y column. So alpha is the transparency of the fill of the bars. And this is a nice trick you can use. So the fill will be red, that's the inside color. The color is black, which is the outside color of the bars. The size will equal 0.2, which is the width of the outside of the bars. And the width will equal 1, so that's the width of the bar. So here the bars will be stacked up right next to each other. Then we can use theme BW to get a nice theme. Scale X continuous will allow you to set the x-axis tick mark locations and labels. And this is important because we're working with a discrete random variable that can only take integer values. And if we didn't put scale X continuous here, the x-axis may have some other labels like 2.5, and that wouldn't make sense because the binomial random variable only takes integer values. Then we have our labels, and we have our theme, and we can get this basic plot. So this is a binomial probability function, or you can also call it the binomial probability distribution because the distribution was a representation of the function. And if we take a look, this is what we have. This is a symmetric distribution. Okay. And we have this different shading of the bars because we mapped alpha to the Y aesthetic. So some people might want to reverse the coloring and use like 1 minus alpha so that you get lighter colors in the middle and darker colors on the outside. But that was question 1. Now in question 2, you have a similar question, but here you're going to generate 1 million random numbers from a binomial distribution with these parameters, and then you're going to use that to plot the empirical cumulative distribution. So we begin by setting the parameters again. N is 30, P is 0.439. And if we want to generate random binomial numbers, we use R binom. And we set, how many do we want? 1e6 means 10 to the 6th. The size parameter is n, and the probability parameter is p. Then we can organize that those random numbers into a table using the table function. Then we can sort the unique values. So the sort function will put things in ascending order. And the unique function will only return the unique values of a vector. Then we can say that CB will be the cumulative sum of the table divided by the length of RB. Okay. So this CB is going to give us the values of the empirical cumulative distribution function. And then we can create a tibble to plot the data. Note that when you define a tibble, and if you don't explicitly have the column names identified, if I just apply vectors like this, then those will become the names of the columns. So I like to usually, specify the names explicitly, but if you don't do that, it will still work, and the names of your column will be whatever the names of these vectors are. So let's go ahead and create the plot. Once again, G is assigned to be a grammar of graphics plot connected to the data M. Then we add geom column with a mapping of aesthetics. The X aesthetic will be the NB column. The Y aesthetic will be the CB column. And alpha, the alpha aesthetic, will also be the CB column. Then we can set these other aesthetics. So there's mapping of aesthetics when the aesthetics are going to be changing with the data argument. And then these other aesthetics, color, width, size, and fill, they're being set. They're just being set to a constant value. Like color will be black, width is always 1, the size is always 0.2, and the fill is always dark green. Now we can use scale X continuous, and we can create a sequence from the minimum of RB to the maximum of RB, going by steps of 2. Then we can get labels, and we can add theme. And this is a plot of the empirical cumulative distribution function for that random binomial data. A couple of things to review here about cumulative distribution functions is that as you go from left to right, they are non-decreasing. So they typically are going up and they approach 1. Eventually they get to 1 or very close to 1. And you see that reflected in this picture. Okay, on question 3, you're going to create some random geometric data. So we're going to let X be a geometric random variable with parameter P equals 0.25. Then we're going to generate 1,000 random numbers from that distribution, and then we're going to plot them in a histogram. So perhaps you should say a bar chart, because a geometric random variable is not continuous, it's discrete, and typically the histogram is used for continuous data. So there may be a little bit of an issue there, but it will still work for what we're trying to accomplish. We want to visualize what the distribution looks like, and I may be using geom histogram, but that is okay. So we set the parameter P is assigned to be 0.25, N is assigned to be 1,000, Rn will be random geometric numbers, so rgeom, where N is N, that's how many numbers you want, and there's only one parameter, prob. For the histogram breaks, we'll go from the minimum of Rn minus 0.5 to the maximum of Rn plus 0.5 by steps of 1. And the reason we do that is we want to be able to capture all the whole range where these bars are happening or where these values are appearing. And we also know that the length of the histogram bar should be 1, because this is a random variable that is a count. It's just 1, 2, 3, 4, etc. And then I can have a tibble. M is assigned to be a tibble. And then I say G is assigned to be a grammar of graphics plot connected to the data M. And then I say geom histogram. And I have a mapping equals AES. And I have that X. So this should be, it should say X here. It still worked, but it should have said X. Okay. Y will be dot dot density dot dot, and alpha will equal dot dot density dot dot. Remember, these dots mean that you're working with a computed aesthetic. So it's an aesthetic that was not a part of the data frame or the data argument necessarily, but when you started working with geom histogram, it would take the data argument and it could compute this. Okay, this is a computed variable or a computed aesthetic, and then we could use Sienna, etc. Here we're using xlim just to control the limits of the plot, and this is what we get. So this is a relative frequency histogram of some geometric data. And it starts off high and goes down. Okay. On question 4, you're going to work with a negative binomial random variable with parameters r equals 6 and p equals 0.5. And you will plot the probability function from 0 to 20. So once again, you begin by defining the parameters of the distribution. R is 6, P is 0.5. Then you can create the data that you're going to use to plot. So M is assigned to be a tibble with columns X and Y. X will be a sequence from 0 to 20 by 1, and Y will be D of n binomials. So this will be the probability function of a negative binomial random variable with parameter size as R and probability as P. And what's happening here is this X right here on the right is referring to this one that was above. And so dn binom will be applied to every element of the X column to give you a new column. And then we can use geom column. So G is assigned to be a grammar of graphics plot connected to the data argument M. And then I can add geom column. And remember, geom column maps the height of the bar to one of the variables in your data argument. So geom column, I say mapping equals AES, the X aesthetic will be X, the Y aesthetic will be the Y column of the data. So that will be the height of the bar. And the fill will also be Y here. So this will give me, I'm going to get now different colors based on the height of the bar. And so here, if you use scale fill gradient n, you can specify a gradient of colors that will match up with this fill aesthetic being mapped to Y. Here I'm using heat colors, which are like yellow, orange, and red. But you could supply your own vector, like you could put C and then blue, green, orange, or something like that. And we may see that later. Okay, then you finish up your plot, and this is what you get. So this one has the feature that you actually have different colors because we use scale fill gradient n, and that allows you to get different groups of colors to be coming out on your plot. Okay. On the next one, you're going to work with a Poisson random variable, and you're going to generate the probability function. So M is a tibble where X is a sequence from 0 to 20 by 1. And then Y is D Poisson, so that's the probability function of a Poisson random variable with parameter lambda equals 5. So Poisson random variables are count variables. They just take values 0, 1, 2, etc. And they're one parameter, which is called lambda. And you see us using geom column again. Now here, I've done something a little bit different. So I still have G is assigned to be a ggplot connected to the data M, and I'm adding geom column. But when I have mapping equals AES, the X aesthetic will be the X variable, the Y aesthetic will be the Y variable, but now alpha will be Y divided by the max of Y. So alpha would usually be a number between 0 and 1. So it's the transparency of the fill. But what if you have a column that you want to map to the transparency, but that column takes values bigger than 1? One way to work with that is what I did here. I take Y and I divide by the max of Y, so it'll always be something that is less than or equal to 1. Now, instead of scale fill gradient n, there's also this function scale fill continuous, and you supply a type, like there's type viridis, and now there's type gradient, and that gives you a different, oops, I didn't want to do that. So I made a mistake here. Here I said the fill was maroon. So I should have deleted this part. This part right here, scale fill continuous, it should not have been there. That was a kind of a redundancy or an oversight on my part. But here we're making the fill maroon and we're mapping the alpha to Y over the max of Y. And that gives us this effect once again where we have darker colors the higher the bar is. And lighter colors the lower the bar is. So this would be an example of plotting the probability function of a Poisson random variable, and you see it's symmetric about the mean, or nearly symmetric about the mean. See, here's 5, but then you also have 4 there. Now we're going to look at the survival function, and this will introduce a new aspect of working with probability distributions. So in the software, there is this argument for the CDF functions, which are like P Poisson, P binomial, and the argument is called lower dot tail equals false, or it's called lower dot tail. That's the name of the argument. The default value is that it's true. So if I want to work with a survival function, which is a probability that you're bigger than something, so it's 1 minus the CDF, one way you can achieve that is by switching lower dot tail to false. Now, when I'm just working with CDF, I don't have to specify anything about lower dot tail because the default value is true. So if I don't say anything, it just assumes the default value. But here, we are working with a survival function, which is a probability that you're bigger than a given number. So I have M as a tibble where X is a sequence from 0 to 15 by 1. And S sub X will be the probability function, not P. This is P Poisson stands for CDF. P Poisson of X, lambda is 4, and lower dot tail is false. And then when we build the plot, we can do the same thing. We say G is a GG plot connected to the data M. Then we have geom column mapping equals AES. The X aesthetic is the X column. The Y aesthetic is the SX column. And here the alpha is the SX column. Now you may be wondering, why don't you do like SX over max SX? And one reason for that is SX is already between 0 and 1 because it's a probability. You still could have done that. If you did SX divided by the max of SX, it just would have made the maximum bar have alpha 1. So it may still be a good idea, but you don't have to do it in this case. And then this is the survival function of a Poisson random variable. Okay. Survival functions are 1 minus CDFs. So they would, as you go from left to right, they would be going down in value and they would eventually get closer and closer to 0. Okay, here's number 7. Number 7 is about drawing an area plot, and this is a very common plot in statistics and probability. So one of the applications of probability distributions is to do a hypothesis test, which is a part of inferential statistics. So you may have some data that you're looking at and you want to know, could this be observed just by chance, or is there something going on that is causing the data to have the pattern that you see? And a lot of those types of questions can be tested by using a continuous distribution, and then the area under the density curve is a probability. And so just like when you were in calculus, the area under a curve was a central thing, here it's also can be an important thing. So here we're going to work with a gamma distribution, and we want to compute this probability that the variable is between 2 and 7, and then we want to create a picture of that. So I can define my parameters, shape, scale, and I can get the limits a and b to be 2 and 7. Then to compute the probability that a continuous random variable is on some interval, you do p gamma at the top value, and then you subtract p gamma at the lower value. So you get the probability that you're less than 7, and you subtract the probability you're less than 2. And what's left over is a probability that you're in the middle. And we can see here that that's 0.53. Now, to create this area plot, you are going to have M assigned to be a tibble, and you're going to have an X and a Y and an XP and a YP. And the reason you need that is you need one XY pair just for the part where the area is, so you use geom area, and then you want another XY pair to get the rest of the curve, even where it was not going to be shaded in. So here we're using d gamma, which is for the density of the gamma distribution. And when we do our GG plot, we use geom area. Geom area will give you the area between a curve and the x-axis. So I say G is assigned to be GG plot, the data is M, and I have geom area, mapping is AES, X is X, Y is Y, and the fill is dark orange, and the alpha is 0.5. Then we can add geom line, which will give us a curve. And no, you can put the arrow here. Okay, so you can add an arrow at the end using last. It'll be an open arrow. Then we can add geom text to display what the area was. And at the end of this process, we get this picture. So this is a nice picture. It's important that, or maybe not important, but it can be useful to know how to make this type of calculation and how to show the plot. Because as you go forward into learning more about these areas, you may be learning about other statistical tests that have a null distribution. And when you try to explain what happened when you were doing the statistical test, you could generate pictures like this one sometimes to help communicate or understand what was going on. So this is definitely a nice plot to be able to make, a type of plot to be able to make. A geom area with a geom line. I'm computing the area and putting it here on the plot. Okay, on question 8, this is just one of these questions is letting you to continue practicing. You're going to generate 1,000 random numbers from an exponential distribution with mean 5 and plot a histogram. So here M is assigned to be a tibble with a single column X, which is random exponential numbers. How many? N is 1,000. Now, they have rate equals 0.2 because 1 over the rate is the mean. So when you think about an exponential random variable, sometimes they specify the parameter as the average or the mean, and sometimes they talk about the rate, which is 1 over the mean. And here we're doing 1 over 5 for the rate, which is 0.2. Then I do G as a GG plot connected to the data M up here. Then I have geom histogram with a mapping equals AES. The X aesthetic will be the X variable. And then I'm using dot density, this computed variable, to be both the Y aesthetic and the alpha aesthetic. So that will give me different shadings based on the height. And we'll work with forest green here. And that gives us this plot. Okay, so these are some random exponential numbers. An improvement here, this got bunched up. I have this caption, and it got bunched up with the x-axis label. Okay, let's go to question 9 and see what we have. Question 9 presents you with a nice opportunity to practice something that's also useful in calculus. We want to plot 3 different beta density functions together. And one of the ways you can go about that is working with expand.grid. So I say M is assigned to be expand.grid, and I supply 3 vectors, x, alpha, and beta. And what expand.grid will do will return a data frame whose rows represent all the possible combinations of the elements of the vectors that you supplied. So here, for every possible value of x, you'll have every combination of alpha and beta. And then we could mutate. When we're done with expand.grid, we can mutate to add another column called Y. So mutate will add a new column to your data. And the new column will be the density of a beta distribution. And you have shape 1 and shape 2 here. Then to create the plot, to get all 3 curves at once on the same plot, one way you can do it is as follows. You say G is assigned to be GG plot, connected to this data M up here. And then you add a geom line. And when you have your mapping of aesthetics, X will be X, Y will be Y, but color will be mapped to as.factor beta. So you gotta, maybe you don't have to do this, but if you say color equals as.factor beta, it's gonna turn this numeric vector up here into a factor, and then it seems to work nice with what comes next. What's happening here with guides is instead of just having a single line on the legend, I'm going to get a full colored in box. So that's an option you have. Notice right here, you can put in UTF codes. Okay, so sometimes you want like the beta symbol to come out. You can work with UTF codes. So Scalable Color Manual will allow you to manually control the colors. And here I just chose Topo Colors. And let's see what we get. So you see there's beta. All right, there's beta because I was using the UTF codes, and I get 3 plots all at once. And you see how here for this legend, you have a whole box. That's where guides came in. So it may be easier to look at the whole box than just a skinny line. But that's one way you can go about getting 3 curves at once on the same plot. Okay, and that can be a helpful tool in thinking about the functions you're working with or the ideas you're working with. Understanding how does something change as a parameter varies. And the last question is the same, except you work with a normal distribution. So the normal distribution is a bell curve. So now we're going to have M is assigned to the expand.grid. X is a sequence of length 1000. You have mu is 0, and sigma will be this vector. And you pipe that to mutate, and then Y will be d norm of X. We have mean is mu, and standard deviation is sigma. So the normal distribution has 2 parameters, the mean and the standard deviation. And remember what expand.grid does, it returns a data frame whose rows represent all the possible combinations of the values of the vectors that you supplied. And so this is one approach to plotting several curves all at once. Now, to get the plot we want, we say G is assigned to be ggplot connected to the data frame M. Then we have geom line. Mapping equals AES, the X aesthetic is the X column, the Y aesthetic is the Y column, and the color aesthetic is as dot factor of sigma. So we get 3 different colors, and then we can use scale color manual to control both the labels and the values, and the name here I can use this UTF code. All right, and let's see what we get. So that allowed me to get a mu here, mu equals 0. So on the UTF codes, sometimes I make mistakes because I may put in like the UTF-32 code instead of the UTF-8 code. So here it didn't come out as sigma. So it may take a little bit of extra work to put in the correct code. So I wanted sigma to come out here. Mu did come out here, but I didn't get sigma there. So I need to do a little bit more work to get everything correct. All right, that's it for looking at the PDF. We're now going to open up the R Markdown file and take a look at some of the smaller details that can help you work on completing these tasks. So I'm going to jump out of here and I'm going to go into my RStudio IDE, which I already have open. Okay. So when you open up your IDE, if you had some previous project going on, you may have all kinds of files open and there may be tabs. So you want to clean it up perhaps. So I'm going to do Control L here. Control L didn't work, so I hit escape, and that's another way to clear up the console. Then I want to set my working directory. So I go to session, and I'm going to go to set working directory, and I need to choose the place on my computer where the file I want to work with is going to be at. And you can see it did that here. This is reflected now in the console. It said set working directory. Don't forget, there's also the get working directory function. And the get working directory function will return the working directory that you have right now. Okay, so I can see here, I'm in test 2, and the file I want is this one, t2solutions.rmd. Okay. So now when you open up this file, one of the issues is it's kind of big. See, you have hundreds of lines of code, and you have 10 different sections. Right? If you have a big file like this one, or even if you don't, if you want to go to a certain line, like right now I want to go to line 1, if you do Shift Alternate G, then you get this go to line box where you can enter the number of the line you want to go to, and see, and that brought me back to the top. So when you open up your file, one of the first things to do is come up here to author, and using the Shift key and the arrow key, you highlight the name that's there. Then you go to the Find Replace tool and you put in your name, Mickey Ortiz. And then you can select all. Now, if that replacement existed in many places in your document, it could be replaced all at once, which can be very helpful. All right, then you're going to run the setup code chunk. Don't forget that when you run the setup code chunk, you may discover that some of the packages you need have not been installed. In that case, you would come down here to install, and you would work to install the package. Okay, now when you have a big file, one option is to fold up the sections. Folding up the sections will simplify your view of what is in there. So this can allow you to get a grasp of the contents of your file, okay, by folding up the sections. All right, let's just review a few basic concepts. This top part, remember, is called the header, and the only required part here is the output. Now, header includes has this use package stuff. That's for LaTeX packages to also be included in your work. Remember, this is the setup code chunk. And also remember that you can navigate your document by coming in here. Okay. Now, I want to show you something that made it easy for me to create this test. Maybe not easy, but easier. Don't forget, you have the option to create and use code snippets. So I used code snippets in creating this test. Those are down here. These code snippets, if you choose to use them, can help you from always having to retype the same code, right? That would be kind of boring or a waste of time. If you create some code snippets, that's going to help you get your work done faster. All right, everybody, good luck on this test, and please contact me as you need help. Bye-bye.